Hello, everyone. This is Will. Welcome to the second part of the intro to miniKanren Hangout number 3. My internet went down hard, so there was some scrambling around for half an hour and things like that. Fortunately, it came back. And fortunately, I wasn't talking for that much longer with the dropped internet. It's actually a little hard for me to tell when I'm screen sharing if the internet goes down. It doesn't normally happen. But we're almost done. So let's just finish off a couple of examples. Or I think maybe 2 examples that got cut off. Finish those up, talk about what's next in store, and then we can end it. So this is going to be a very short section, unless people want to talk about questions, which we'll probably take offline. Then we'll do next time. We'll have the beginning with the questions section. All right. So let me go back to Emacs, screen share, and I'll put this transcript in GitHub with the rest of the information. All right. And I think we had gotten to the point where we were talking about shadowing and lexical scope and free and bound variables and let binding and let star, lambdas and all those sorts of things. And we had talked a little bit about environments, and we had kind of traced through evaluation of expression with nested lets and kept track of how the environment grew and how we might have shadowing of this X, for example. Right. So we had gotten past all that, I believe. And so we're almost done. I think about where I dropped was here. So let me just go through this again real quick. So here, some nested lets. And one second. Oh, I actually have to, yeah, that's a transcript. It's actually not my Emacs session. So, expression. So we've got 2 nested let expressions, and we can play our environment game like we did before. So we start out with the empty environment. And then inside the outermost let, X is going to be bound to the value of the expression plus 2, 3. That's going to give us 5. And then on the innermost let, this X is going to be bound to, and that is going to shadow the old environment, which was X bound to 5. Okay, so this X is the innermost binding. We look inside out, and we find it's bound to this X, bound to 7. So therefore, that's the value of 7. Okay, so we have a simple example of shadowing. And I think where I got cut off was just very briefly pointed out that we can avoid shadowing if instead we were to rename consistently the variables so that each variable binding only appears once. So here we have 2 different bindings of X, but instead of talking about shadowing, what we could do instead is rename X to be, say, Y. And then we have to rename this occurrence of X to be Y as well. And then our environment would look like this instead. Now we have Y bound to 7. We still get 7 back, has the same behavior. But the idea is that in this case, we don't have to worry about shadowing at all. Okay, so shadowing doesn't hurt us, and it makes clear, I think, some of the issues of scoping. But we don't actually need it. We could rename the variables consistently. And if we rename these variables consistently, that's what's called alpha renaming. So we just have to do a consistent renaming. And we just have to make sure that we follow some rules when we rename these variables to make sure that we don't accidentally change the wrong variables. And so one way we could do this is make sure that we pick, essentially gensims or generated symbols like we saw before. So if you name like this, that we're sure doesn't appear in the symbol. We could have some, or in the program, we could have some sort of counter we keep track of, and we have some sort of generated symbol, and we're making sure that this symbol hasn't appeared anywhere else in our code. The computer can do this for us, and therefore we're guaranteed that we're not going to accidentally pick the wrong variable name. And Scheme has, or at least Shea Scheme has this thing called gensim. So I can say gensim y, and it gives us this special unique symbol. So therefore, we can use something like gensim to generate those variable names if we want to. If we were writing a program that wanted to do alpha renaming, we could use something like gensims, or we could do our own gensimming by passing our own counter around and so forth. But anyway, the point is, we don't have to really worry about shadowing. We could instead go through the code and rename the variables consistently. And there's a set of rules on how to do that. Now, I'm not going to get into that right now, but that's something we might want to look for in the future. But basically, everything we do, we're going to handle shadowing. It's not really a problem. We can just extend the environment. And if we handle our environment right, then we get the shadowing behavior automatically. We can handle that correctly. So that's not going to be really a problem. Okay, so we saw today, we looked a little bit more at let and let star. That was a new form for us, which turns into nested lets. We talked about the difference between let and immediate application of a lambda expression, which are called left lambda. And we also talked a little bit about macros. We saw that we can have macros with ellipses, these ... dots. And so we created an extended version of our let macro that used the ... dots. We also created our own version of let star, which was a recursively defined macro. And we got into discussions of lexical scope, free and bound occurrences of variables. We saw that if you have a free occurrence of variable in the entire, or a free variable in the entire expression, you could get an error when Scheme tries to look up the variable. It's going to say it's unbound, like that's a free occurrence of y. Y is not bound. But of course, we can bind it using lambda, let star, any of the binding forms. There's let rec, there are a number of binding forms, and we can introduce new binding forms if we want to. And in fact, miniKanren introduces new binding forms. miniKanren has a binding form called fresh, for example, that introduces something called a logic variable. So that's a binding form. And we're going to see that fresh itself is a macro. Fresh is something that looks a lot like let. And so our definition of let will look something like the definition of fresh. And we got into the notion of an environment, where we could think about having a list, let's say, that'd be one representation of environment that shows the binding between variables and their values, like y and 7, x and 5. And we also talked about how the fact that, if I go back to my transcript here, that we're not actually modifying the old version of, this is of the bindings. Let's see, where's my lists? I think I showed this one, right? Oh, did I show this one? Maybe, I don't know if I showed this one or not. Okay, yeah, I did show this one. Okay, so with the list, right? So this is really important to understand, this example. This is critical. That we can, have two x's that live together and they have different values. So this x here refers to the innermost binding of let. This x here refers to this outermost binding of let, of x to let. So therefore, this innermost x has the value of 7. This outermost x has the value of 5, and that's completely consistent. That's not a problem. So when you look at a value, when you look at a variable reference, the questions to ask are: is this a free occurrence, or is this a bound occurrence of the variable? And if it's a bound occurrence, where is it bound to? What's the binding form it's bound to? And that's how you have to, you have to be able to reason about that to try to understand what's the value of the variable. And this leads to this idea of environment. So next time, what we're going to do is we're going to use our pattern matcher, pmatch, and we are going to write some programs that will deal with environments and free and bound variables and things like that. And so we're going to be able to write some programs that'll take a scheme expression and will tell us whether or not a variable is free or bound, or will tell us what value in the environment the variable is bound to. And this is important in order for us to write an interpreter, because a scheme interpreter is going to have to keep track of this environment so that we know what the value of x is. Whenever we have an expression involving x, we need to know what x is bound to. So we have to look up x in the environment. So one of the more interesting and important parts of writing an interpreter is dealing with environments, dealing with the scoping, dealing with schemes lexical scope. And at some point, we'll look at another way to do scoping called dynamic scope, which some older versions of Lisp use, and sort of why newer versions of Lisp tend not to use that, and the problems you run into when you use dynamic scope, or can run into when you use dynamic scope. So we'll see that the way scheme handles scope isn't actually the only way to do it. There are other ways of handling scope, but there is a good reason scheme handles scope the way it does, and we'll see what the differences are. And we'll see that once we write an interpreter, we can change the behavior of the variable lookup to get different scoping behaviors by just changing one line of code. In fact, just changing one character in the interpreter, we'll be able to get different behavior. So that's what we're going to look at next time. And of course, if you have any questions, let me know, or show up next time, next Hangout. If you're watching this video, you can show up next Hangout, and we can talk about any questions people have at the beginning, and then we'll dive into writing some code that deals with variables, free and bound occurrences, lexical scope, environments, and all that. And then once we have a good handle of the environments, then we can go ahead and write our interpreter. And at that point, once we actually have a good understanding of scope, the interpreter is much simpler, because the tricky parts of the interpreter, for the most part, have to do with scope and variables and variable lookup and environments and so forth. So if you really understand the environment stuff well, then the interpreter becomes much easier to understand. And if you remember, we had lambda calculus, which had three parts. We had variable lookup, we had lambda or abstraction, and then we had application. Those are the only three parts that we needed to have a Turing complete language where we could express any form of computation. So of those three, one is variable lookup, and then another is lambda. And so lambda is our call by value lambda calculus interpreter is going to be about extending the environment with the variable binding. So lambda is a binding form, and then we have variable reference. And then it turns out that the application form is, also is involved in the environment. Has, in order to implement application correctly, you have to know how to look up a variable in the environment and things like that. So the environment's going to turn out to be sort of the key aspect that holds together our interpreter and sort of makes the interpreter interesting. And so when you're looking at an interpreter for a language, you really want to understand how the environment works, how variables work, how variable lookup works. And we'll also see that once we get to logic programming, that logic programming has a different notion of variables. There's still this notion of lexical scope and environments, but there's, in some sense, a more sophisticated notion of what it means for a variable to have a value, because we'll have these things called logic variables, where you can talk about the logic variables or manipulate logic variables when they have no assigned value at all. It's a little bit different than normal value, a normal variable in scheme. But we'll see that once you actually dig into the implementation, there's still this notion of lexical scope. There's still this notion of environments, and that basically we're adding one level on top of the normal scheme environments. It's not that we're throwing away everything we know, it's that we're just adding a little bit more to that notion. So that's what we're going to do next week. We'll get into using our pmatch and pattern matching against different types of scheme forms, different binding forms, and dealing with environments and variables and lexical scope. So that will be basically one step removed from being able to do our interpreter. And the interpreter is where it really, really gets fun. And once you understand how to write a Scheme interpreter in Scheme, that opens all sorts of possibilities. And that's when you really start understanding how a language like Scheme works, or basically any language works. And if you can write an interpreter for it. So that's something that I was a professional software engineer for a number of years before I really knew any of this stuff. And it would have been very helpful, because there were times where I did something equivalent to writing an interpreter or writing a compiler, but I didn't realize it at the time. So, I went through all of my undergraduate education without ever writing an interpreter, except for, sort of my own personal interest writing things on my own. But if you write a Lisp interpreter in Lisp, I think you'll see that has some real advantages in sort of the Lisp syntax and the way Lisp is constructed, and with quotation and things like that, that makes it very simple, very short and elegant, but still gives you tremendous power. So this is, I think, one of the great programs in the history of programming is a Lisp interpreter written in Lisp, and that's we'll be coming up to that pretty soon. Okay, until next week, see you then. Sorry for the interruption due to internet going down. I guess these things happen. Hopefully internet will stay up next time. If you have any questions, please let me know. See you then. Stop in the broadcast.